Remember, I think it was in my first lecture, I said that when we change from Galilean physics to special relativity, we will have to give some things up. And we've already discovered that we have to give up the idea of simultaneity. Simultaneity is now a relative concept, not an absolute concept. And there are some other things which we have to give up. And one of them is the idea of the length of a piece of chalk or some rigid body. Okay, we think in Galilean physics we think of that as something which everybody will agree on, but in fact it's not. And similarly, time intervals, clocks, behave differently when they are moving. And these are rather weird effects, and I'm going to describe them in a minute. But first I'm going to draw a picture for you, which I could have done earlier actually, but I'll do it now anyway. It's called a space-time diagram or a Minkowski diagram. So we draw the time axis here, and so that's t, and that's x. And in this diagram, I'm going to completely ignore y and z. Because I can't draw in 4 dimensions. And I might as well drop both of them because they're, for the special Lorentz transformations, they don't play any significant role. And I'm going to choose units in which the velocity of light is 1. So I can measure time in years, and I might measure space distance in light years. Okay. Or I could measure time in seconds and space in light seconds. Just to give you a sense of the scale of things, many of you are simply shockingly too young to know this, but when the astronauts landed on the moon and you could hear them talking to the mission control, there was a delay. And it was 1 second, approximately. So the time it takes light to travel between the Earth and the moon is approximately a second. And you could see it, or you could hear it, right? The time it takes light to travel to the Earth from the sun is about 8 minutes. The nearest star apart from the sun is about 4 light years away. It takes about 4 years. Anyway, it's quite natural to choose the coordinates, the units in such a way that, in this case, the velocity of light, you see, if you have a photon here, it's going to travel like that, isn't it? 45 degrees. So that's quite natural, nice thing to do. So effectively, you've set c equal to 1. It's an old trick in physics, isn't it? If you don't like something like c, you make it 1. Now the question is, where, in this picture, where is the t primed axis? And where is the x primed axis? You see, this picture is called a spatial picture. I've not drawn time in here. Okay, time, you can't see time in here. I did draw a little clock to remind you that each frame has its own time, but I haven't drawn time as an axis. I've just drawn the space. Whereas this is a space-time picture. So we can ask, where are the other axes, t dashed and x dashed? Well, let's just play around a little bit. If you want, we're still in S at the minute. You want to know what are the, if you take a particular event, so it's happened at a particular time at the origin, at x equals 0. What are the events that are all happening simultaneously with that? Well, there'll be all of these events along here. So that collection of events are simultaneous in this frame of reference. Okay. Or you could take an event that happened at t equals 0, but somewhere else, and you can say, suppose you don't move from that position, right? What are all the events that have the same position as that? In other words, what if you're a particle there, what happens to you in this picture? Well, it's right. So that's called the world line of that particle. That's called the simultaneous space of that event. Okay, so that hasn't answered. Okay, that hasn't answered our question yet. Namely, where are the other axes? Let me just check my notes to make sure I don't get this muddled up, because I know that sometimes I do. So in S dashed, so this was an instant of time here. What about the instants of time in S dashed? So suppose we take constant t dashed. You see, when I drew this line here, I was taking constant t and varying x. Suppose I take constant t dashed. Well, t dashed, if that's constant, t dashed is gamma x minus v, t minus vx. In the Lorentz transform, it's t minus vx over c squared, but c is 1. So it's just this. So if that is constant, then this is constant. So t minus vx is constant. And in particular then, the x dashed axis, you see the x-axis is where t equals 0. Right, that's the x-axis. So the x dashed axis is where t dashed equals 0. And that's where this equals 0, right? And so the x dashed axis will be something like that, where that angle there depends on that letter there, okay? And then you do the same thing. The t-axis was where x was 0. So the t-dashed axis is where x dashed equals 0. But x dashed is gamma x minus vt. And so now you've got x minus vt equals 0. Instead of t minus vx, you've got x minus vt. So the t dashed axis is exactly the reflection here. It'll be somewhere up there, where that angle is the same as that angle. So it's a sort of anti-rotation, right? If it were just a straightforward Euclidean rotation, you'd have gone over there. But this is a squishing up of these two. And you can use pictures like that to get a very good qualitative understanding of problems with bombs and airplanes and things like that, if you're careful. I'm going to come back to these pictures tomorrow or maybe the next day, probably tomorrow. But let me do what I promised first and say a little bit about these strange effects of length contraction and time dilation. Okay, so first of all, length contraction. The calculation is very easy, just straight away from the Lorentz transform. What we're going to do, I don't think I need this one anymore, so I'm going to rub that out and just get back to having 2 frames of reference only. The usual configuration. I think I'm using V. Yes, I am. I'm back using velocity. And what I'm imagining now is that there's a rod. It could be a meter rule, okay, made of something really fierce like steel, right? Builders use them, don't they? They don't have wooden rulers, they have steel ones, because otherwise they'd quickly fall apart. So you've got a rigid rod, and you have it lying along the axis, and it's fixed in, it's stationary, it's not moving in this frame of reference. So and it's got some length, right? It's got some specific length, and we're going to call its length L dashed, because it's stationary in S dashed. So S dashed is just an observer holding a steel rod. And of course, from the point of view of S, that rod is moving away. So S wants to, so the question is, S wants to measure the length of that rod. And so for what S has to do, it has to, so what we do is we say that x2 dashed and x1 dashed are the ends of the rod in S dashed, right? So that's in the x dashed coordinates, x1 dashed, and that's x2 dashed. Now, in order to measure the length, in order for S to measure the length of the rod, S has to find out where the 2 ends of the rod are in the x coordinate at the same time, okay? There's no point in S saying, now the near end of the rod is there, and then I'll have a sandwich, and then I'll see where the far end of the rod is. That won't tell S how long the rod is. S has to say, at the same time, in S, where are the 2 ends of the rod? So x2 and x1 are the ends of the rod in S at time t. In other words, you're measuring, S is measuring the 2 ends of the rod simultaneously. That's what you do when you measure the length of something. And then you just write down the Lorentz transform, and you get x1 dashed is gamma x1 minus vt. x2 dashed is gamma x2 minus vt. And you subtract, and you get that L dashed is gamma L. Just by subtracting these two, right? This minus this is L dashed. It's the length of the rod according to S dashed. If you subtract, then you've got this gamma, of course, and you've got x2 minus x1, that's L, and these two cancel because you've measured it simultaneously in S. Or in other words, L is L dashed over gamma, which is L dashed times the square root of 1 minus v squared over d squared, which is less than L dashed. Okay, everybody happy with that? If this is true, then this is true. Gamma is the inverse, is the reciprocal of that, so L dashed over gamma is L dashed times that. That's a number less than 1, and so L is less than L dashed. So there's no way out of this. That rod, if it's a meter long in S dashed, then S will say, no, it's not a meter, it's short. And the amount it's short will depend on the relative velocity. So that's called the Lorentz-Fitzgerald contraction. It had been discussed before Einstein's special relativity, but in a different context. Lorentz proposed that when a physical object moves through the ether affected that object by making it contract in the direction of motion. His argument was that physical objects are made up of compounds which use electrostatic forces to hold them together, which is partly true. And so the ether affects all those forces in such a way that the object contracts by this amount, you see, which is very clever that he could do that. But so it was the right equation, but the wrong philosophical approach, right? If you abandon the ether, then you've got to, this contraction happens, but it happens because of the transformation that you're using, not because of anything else. Okay, that's length contraction. I don't think there's anything else I need to say about that. Is there, before I move on to time? The length of, I want to say one more thing, the length of the ruler is biggest, so the ruler is longest in its rest frame, right? It gets shorter according to everybody else. It's longest in its rest frame, and in its rest frame, this is called the proper length. Okay, and so S dashed will be having you know, a FaceTime discussion with S, and S dashed will say the proper length of this ruler is a meter, and S will say, nah, well, I'm sure you think it's a meter, but to me it's not, you see. But everybody knows the frame in which it is at rest, so everybody agrees on what the proper length is. It's just not what they see as the length of the ruler. Okay, that's that one. What about time then? Let's do time dilation. So the Lorentz transform affects clocks as well. And then, so what we do is this time we're fixing a clock in S dashed. Here it is. There's a little clock here. And we imagine it's ticking, I don't know, every second, let us say, it emits a little flash of light or something. It's got a tick. And it's ticking in such a way that S can observe those ticks. So what we're going to do is we're going to take two ticks, two successive ticks. So maybe they're a second apart, but it doesn't have to be a second. Are T1 dashed and T2 dashed. So that's, we're all in S dashed because the clock is at rest in S dashed and we're observing it from S. We imagine, in fact I've drawn it at the origin here. It doesn't have to be at the origin, it doesn't make any difference. So I'll amend this drawing a little bit. It doesn't have to be at the origin, that's, I mean it could be, but doesn't have to be. We'll imagine that here is our little clock T dashed, okay, not there. It could be there, but it doesn't have to be. So it's somewhere there. And we want to find out what S thinks of this. So we use the Lorentz transform in its inverse form. T equals gamma T dashed plus V x dashed over C squared. So that's the inverse transform. You remember we've wrote them down first of all as T dashed equals something involving T. And if you invert that, this is what you get. So in particular, T1 dashed, sorry, T1 is going to be gamma T1 dashed plus V x dashed over C. And T2 is going to be gamma T2 dashed V x dashed over C squared. And I have not changed this because the clock's not moving, right? It was here, x dashed. And in S dashed, it's not moving. And then you do the same thing. You subtract, and you get T1 minus T2 is gamma T1 dashed minus T2 dashed, which is greater than T1 dashed minus T2 dashed. Gamma is greater than 1. So if this difference here was 1 second, then this number is greater than 1 second. Okay, so from the point of view of S, the clock there is ticking slowly. Actually now, not when Einstein was doing this, of course, but now the atomic clocks that we have are easily accurate enough to detect this. There's absolutely no question about it now. And so, I mean, I'm not saying that having an atomic clock, well, in a sense, we all do have all sorts of atomic clocks because you can use atoms as clocks. That's why we call them atomic clocks. But the ones that are used for timekeeping, very high precision timekeeping, easily see this property. Now, there's quite early on, the following observation was made. I'll use this board. And this is where we show how special relativity really does get clever. So I don't know when this was first observed. I'm sure we can find out by Googling around a little bit. So here's the Earth. And over here, quite a long way away, is the Sun. And it's shining all sorts of things at us. And in particular, not just photons, but it spits out very high energy particles. All stars do. It's not just our sun that's this unfriendly. And that's actually, by the way, that's why we need our atmosphere. If we didn't have an atmosphere, the radiation intensity on the surface of the Earth from the sun would be too high to support the sort of life that we know about anyway. And indeed, when astronauts, when they first started studying the effect of being in space on astronauts, there's an incredible photograph, a very, very close-up photograph of the helmet of an astronaut. And you can see, if you look very close, I presume it's an electron microscope or something, you can see where these particles that are coming in have whacked into the helmet and deformed the metal. Just, oh, they're very high energy particles. They're referred to rather generically as cosmic rays. And it's one of the problems that people are going to face if we manage to send people to Mars. It's going to be a serious issue, how to protect them from these things. Now, the atmosphere protects us. I'm going to draw the atmosphere like this. Of course, the atmosphere is thinner than the line of chalk here, but let's, give me some artistic license. What happens is that a cosmic ray, it's about, I've got it written down here, by the time you're about 20 kilometers up, so that distance there, It's about 20 kilometers. Bits of atmosphere above that, and it gets thicker and thicker, of course. Most of the cosmic rays smash into some molecule in the atmosphere at about this altitude. So up here, there's a collision at 20 kilometers up between one of these high energy particles and I don't know if it's an oxygen or a nitrogen, maybe it doesn't matter, some molecule in the high atmosphere. And as a result of that collision, an object called a muon is produced. Maybe some other things too. I don't know very much particle physics, but certainly a muon is produced. And these muons, we know about muons because we can make them in the laboratory and study them. And they have very short lives, poor little things. They only live, the rest frame mean life, so the average life before the muon falls apart is something very small. It's 2.2 times 10 to the minus 6 seconds. Right, so they fall apart quite quickly. So they're created 20 kilometers up, but very quickly they fall apart. But we observe them down here on the surface of the Earth. We see them. You can actually detect these muons that were created 20 kilometers up, and we know from experiments with muons in the laboratory, same animals, that they die very quickly. And even if they were moving at the velocity of light, they couldn't possibly travel 20 kilometers in that time. But we see them. So the question is, how? So any answers? How do they make the journey?
Because it is lifetime from its perspective.
So from we look at the muon, and it's moving, right? And so its clock is going to go slowly. And so although from the muon's point of view, its lifetime is that, if it's moving fast enough, its biological clock, if you'll forgive the joke, is going slowly. And so if it's moving fast enough, we will think that it lives for longer. And in fact, it's easy for it to move fast enough without exceeding the velocity of light, so that this lifetime is stretched out and it lives long enough to get down to sea level. Okay? So that's our explanation of how the muon gets to sea level. We think its lifetime is being stretched because of the time dilation effect. So I've got an exercise here, which is number 22. What is the muon's explanation? The muon doesn't think that its clock is running slow. For the muon, it only has 2.2 times 10 to the minus 6 seconds. But it sees itself rushing down towards the sea, and splosh, it hits. How does the muon think? How does the muon explain that it gets down to sea level? Any suggestions? Yes?
It's going very quickly, quick enough to reach.
No, it can't. It can't. It's got to travel 20 kilometers in 2.2 times 10 to the next seconds,
Right.
and it can't do that below the velocity of light. But there is another explanation.
Distance is small.
Sorry?
Distance from muon.
Yeah. For the muon, the muon is stationary, and the Earth is moving towards the muon at a high velocity. And in particular, the thickness of the atmosphere is moving towards the muon at a high velocity. And so the thickness of the atmosphere is contracted. And the muon thinks, oh, that atmosphere is not 20 kilometers thick. It's much less than that. I've got plenty of time to get down to sea level. Okay, and so you can see how, as I mentioned during the break, both the muon and the physicist in the laboratory at sea level, they both agree on the outcome, namely the muon gets down to sea level. But they have different explanations. The physicist says the muon's lifetime was extended. The muon says the atmosphere is not 20 kilometers thick. And those two effects beautifully fit together to give the same effect, the same overall effect. We're all, I think, familiar with the fact that we've got a very good global positioning system now on the planet. And if you're hooked up, if you have a global positioning system device, it will tell you where you are to within, I think if you step to one side, it can detect that. I mean, it's really very ridiculously accurate, okay? And it depends on a network of satellites called the GPS satellites, and they orbit quite high up, so much higher than these poor muons here that given birth here. They orbit at 20,000 kilometers. They're very high orbits, these satellites, and so and they're moving quite fast. They're moving at 14,000 kilometers per hour. So these GPS satellites, the orbital motion is 14,000 kilometers per hour. And so there'll be a time dilation effect. I know they're not moving in this sort of way relative to us, but there's still going to be a time dilation effect. And if what it turns out is that their clocks, the clocks on these satellites, lose 7 microseconds per day, which is quite a lot. Okay. Actually, there's another effect, even more amazing, that because the clocks on these satellites are very high up in the Earth's gravitational field, much higher than we are, they gain due to an effect, essentially the equivalence principle. It's one of the effects it's essentially one of the axioms for general relativity. So there's a general relativity effect, which means that these satellites gain 45 microseconds. So special relativity makes them lose 7 microseconds per day, and general relativity makes them gain 45. Anyway, so they do some funny stuff, and that's easily, if we did not allow for that, right, we would not have the accuracy for the GPS system. It would be hopeless. It would be miles out, okay, if we didn't allow for these clocks having a different time rate. So it's only because we know that, it's only because we know not only special relativity but also general relativity that we're able to have an accurate GPS system. So if somebody says, huh, what did you do at the school? Were you wasting your time doing some silly piece of mathematics? Yes, you say, I did some special relativity, and your GPS system depends on it. Okay, so it's one of the few occasions when something that we depend on, a GPS, really does use some of this beautifully exotic mathematics. Okay, as I say, I think I've got time to start the next section. So the topic's proper acceleration. I'll explain what proper acceleration is in a little while. It turns out that when we're working through some of the calculations to do with acceleration, we're going to need some formulae satisfied by the gamma function. So it turns out that gamma v is the same as c times the square root of gamma squared minus 1. Okay, that's one of the things that we'll need. It also turns out that c squared d gamma is the same as gamma cubed v dv, and d of, if you differentiate gamma v, that's the same as gamma cubed dv. If I didn't make a mistake. Yeah, that's correct. So these are little identities that the gamma function satisfies, and I've just put them in as an exercise. I'm going to need them, and so at some point I'm just going to say, but this is equal to this. Why? Well, so this is just very elementary algebra. Remember that gamma depends on v in the following way. So you can just easily, please just check these. It will be good practice for you, and I'm going to need them. So what I will do is start us off. As I say, I'm not going to get very far because I don't want to rush because it would be too confusing. So I'll just start us off, and then we'll start again tomorrow and do this again more slowly. So what I'm imagining is the usual configuration here, and I've got a particle. The velocity of s dash relative to s is going to be v1. And I've got a particle here, and its velocity relative to s dashed is v2, and its velocity relative to s is v. So right, so far nothing special happening. You've seen all that before, but now I'm imagining that, of course, v1 is a constant, right? This relative speed of the two frames of reference is a constant, but I'm going to allow v2 to be changing. I'm not imagining that v2 is a constant, and so therefore v will also be changing. Okay, so v2 and v will be changing. So this particle will be accelerating. How do we analyze that acceleration? Now what I'm doing is that I'm imagining that this frame S at a particular instance, at a particular moment, this frame is the rest frame of this particle. So this particle at a particular moment, it has a frame that's traveling with it at that whatever speed it's going at. That's the speed that the frame is going at. The particle is accelerating, so after that moment its speed is greater than the speed of the frame, but at that one moment that was the rest frame of that particle. So momentarily we have v2 will be 0 and v will be v1. So momentarily this is at rest, v2 will be 0, and the velocity of this with respect to this will be that. But that's only for one moment. We can't keep the frame of reference with the particle because the particle's accelerating, so it leaves the frame of reference behind. But it's still useful to have the concept of an instantaneous frame, rest frame for that particle. Don't call it the rest frame, only call it the instantaneous rest frame. Okay. And then you use the formulae that we've got. Namely that v equals v1 plus v2 over 1 plus v1 v2 over c squared. And we start work. And we're going to end up with a, and maybe I'll I don't know how much of this to do because there's several lines of calculation. Yeah, I'll stop. I won't do them today. I'll do them tomorrow. But I'll tell you what we're heading towards, and then we'll stop for now. We're heading towards the definition of proper acceleration. And so that's going to be, so what do we mean by an acceleration? What we're going to do is we're going to say that the acceleration that the particle itself measures in its instantaneous rest frame. So in the life of this particle, it's accelerating. At any moment, it's got an instantaneous rest frame. In that rest frame, it's got an acceleration. That's called the proper acceleration. Okay, and I'll show you how to calculate it in terms of all of these numbers tomorrow. And we will look at a particular case where we've got a particle which is travelling with constant proper acceleration. It doesn't have to be constant, right? But if it is, it turns out we can solve the equation and get quite a nice result.